welcome to the second part of the morning session. And so my name is Antonio Politi, and I'm going to introduce the first speaker, Andrea Orlandi from Lamma. And so, please.
Well, thank you. Good morning. Yes, I'm Andrea Orlandi. I'm a researcher of Consorzio Lamma. And, my talk has a double goal. The first part to make a wide clarification of some points of numerical weather prediction and climate prediction, and then to see an application in the context of flow water models, and I will explain better the elements of this work later on. So let's go. Weather prediction is summarized in this interesting phrase. Well, you must imagine a sphere of quite large, covered by a mixture of gas, which rotates around the sun, nuclear reactor, and then the meteorologist must observe sufficiently the system, and then, on the basis of the observation and of the model that he disposes, must try to forecast in 1 day, 2 days, 3 days. Well, which are the scales of the system? Let's begin to look at the scales. Sorry, the mouse. This is 1 year of cloud images. I ran quickly. You see here many dynamics running under your eyes. The air rotates. And then, as an example, you can see here, sorry, you can see, oh yeah, sorry, the game is not playing as I wanted. You see here, in the region near the equator, a pulsating activity, which is convection. Then, if you go at the high latitudes, north and south, you see different dynamics, in which you see vortexes, evidenced by the clouds, which are pulsating with a different time scale. And if you go still ahead, here, the season of the hurricanes of the northern hemisphere, you can see several hurricanes that occurred near the west coast of the Africa and then travel towards the United States in this track. This is a hurricane, and then you see other again. Let's stop this. I lose also too much time. The dynamics are moved by the energy coming from the sun, which activate the dynamics through thermal gradients. And this is the main source of energy. And here we have a nesting of dynamic scales. So we have the planetary waves, you have seen them in the imaging. Inside this hydrodynamic instability, trigger other dynamics. Inside this dynamics, other hydrodynamic instability trigger dynamics linked to convection. In the tropical area, you have the Hadley circulation, which has the pulsating convection that you have seen in the image, in the video image. So these are the scales, and climate, larger times for the scales, obviously. These are the meteor, and these are the climate. Here, through the average temperature of the Earth, you can see the larger scales of the climate. If you make a spectrum of all these, you find many of these dynamics comparing here in the spectrum, and you can recognize the perturbation here, 3-7 days of time, of classical time. Here we have the convection and obviously the turbulence. Here, as an example, we have glacial and interglacial cycles linked to the forcing instead of forcing fluctuations of the energy from the sun. Numerical model, all those scales, how can one cope with all those scales that are coupled together by nonlinear? You recognize here the ocean, the atmosphere, the turbulence, and the convection, and here we have the climatic scales. Predictability by the models, it is evidenced here. If you are interested in the few first days, you have the highest possible predictability, then the time scales of land and ocean influence the prediction over longer time scales. And if you want to make weather prediction, you must make this operation. You are interested in these target scales. These are almost constant for you, and these are the scales that you need to parameterize because you cannot model everything. So under the subscale, you must parameterize.
You can turn the slides like this.
This is the scale of a weather prediction model. You have the explicit dynamics and you have the parameterizations of the physics. Climate, you make a jump in this state. This is the target scale. These are the target scales. This is the part that you need to parameterize or schematize in something way. Something is relevant to be modeled as a stochastic noise, and this is the longer time scales which you can consult almost constant. And this is the scale for the model. You must couple the atmosphere with the ocean, which is the main time scale to be modeled, and you must couple with a dynamic interaction between the two if you want to make correct climate prediction. And so here, the landscape is this one. Atmospheric modeling is mainly an initial value problem, while climatic modeling is mainly driven by boundary conditions. We can have a picture of this element by considering the approach that has been developed since the 90s of the last century to cope with the errors unavoidably contained in the initialization and in the running of the models to predict the atmospheric dynamics. So instead of the traditional single deterministic forecast, one learns a number n of similar runs, differing only by slight perturbation the initial conditions. The spreading of this ensemble is a measure of the error that one commits in performing the forecast. And this error depends on the methodology of the day. So you see here the same day on 2 different years with a lower predictability in the 1994, and the 7th year, the following year, you have a larger predictability. So you see here there is a variability also on the spreading of the ensembles, and so you can summarize all in this way. The meteorological prediction is based on a sharper definition of the initial state, but its evolution in time is linked to the spread due to the chaoticity of the system. If you are interested in the climate, you are interested in the manifold on which the external forcing obliges the system to remain. If you can't change the external forcing, you change the structure of the manifold and you have a different climate. But the meteorology has a higher level of predictability thanks to the data assimilation. What are the main elements of a correct weather forecast? We have an analysis which is composed of the observation, which must be as more complete as is possible. And today we dispose of a long observing system, which is a very wide enterprise, which allows to have data from the world globe and from many observing needs. You must use this data to initialize the system, because we have seen that metrology is an initial condition problem, but we must remember that we have, due to the nonlinear character of the equations, we have a strong sensitive dependence on initial condition, but we have also what is called the metrological butterfly effect. What is this one? This one is linked to the fact that when you make a data assimilation, you can assimilate a correctly, more or less correctly, initialize a range of scales. The scales that you are not able to initialize gradually make a growing of the error that you have and perturb your model unavoidably. So you have a thin predictability, also linked to the fact that we have a wide range of scales that not all are under the control of the system of data assimilation. Obviously, we have a model that must be as more complete as possible, and we can see here that in order to perform weather forecasting for the next 12 to 6 hours in this point, one should put the data in this area. You see here latitude, and you see here 30 degrees, and you see here 60. So it's a quite wide belt in latitude. Well, if you enlarge the time scale in which you want to go, you arrive to 1 week to 2 months. You need to have the data from the world globe. This is another way to see the same position. If you need to make forecast in the area, you see that the time forecast you can cover grows within the area. And you see another thing, that the observations are not evenly disposed, but are very irregularly disposed. So, how to initialize the system? One takes in account that the data to use are the observed data and the numerical model. But we have errors. One result must pass through a probabilistic view of the problem, and the probabilistic view brings to this type of approach. You have bias and statistical invariance. So the initial state, which is 6.0, which is one of the states of the system which is in absolute not unknown and not possible to be known except for the observation which are affected by errors. So you must describe the situation with a probability distribution which is conditioned on the observation. And is composed through the Bayes theorem by the prior, which is the precedent information. In a forecasting chain, you have the forecast of the preceding cycle, and so you can use the information from this as a prior. Then you have the information about the data observed, and then you make this operation. If you are able to hypothesize that all is Gaussian, you can transform these probabilities in Gaussians, where the efforts are described by the matrices of correlation, which are added for the observation and B for the model, for the background, and this is here. The analysis, which is the best estimate of the initial state of the forecast, is this one, and can be written in this form. The gain matrix depends on the approach that you use to make the computations, and there are development approaches, interpolation, variational, which require to minimize this, which is the cost function approach. But you can also exploit the model in another way. Considering the fact that the model can describe the evolution in time of the system, and you can enlarge the assimilation, and not assimilate only in one time, but using the data from the model in an interval. In this way, the probability has this structure, and you must enforce also that part in the computation. One approach is to use carbon filters, which allows to compute the evolution of the model with the forecast stage, and then updates all the metrics needed for the computation of the initial state. This is strange. The image, sorry, but it's the same. The image is the same. This is the most crowded slide that I have, but it uses the decomposition in Gaussian. We have the Gaussian of the observations, we have the Gaussian of the background, and here we have the transition probability, which can be modeled in two ways. One can model it as a delta of Dirac, and we have a strong constraint. And to enforce this constraint, you can use, for example, the Lagrange multiplier approach. Instead, you can make a weak constraint and model the uncertainty with the one. This is the way to construct the initialization via variation method, and we can also remember that this is very similar to this selection approach. And in reality, these two together and some over the wall path may allow emulation with path integral of the data assimilation problem. This is the schematics of the various data assimilation approaches, and it must be told that when the models are linear and the statistics are Gaussian, always but when the models are nonlinear, the complexity of the system increases, and you must resort to different approaches, which are generalization, but which are much more approximate. As an example, is extended with approximation linked to the differential, the first order differential on the matrices in the extended Kalman filter, and in order to reduce the dimensionality of the problem, it is used the ensemble Kalman filter that we will see in the application part. And so we are arrived to the fact that the geophysical prediction is really a grand challenge. So as von Neumann formulated it when they constructed the meteorological project, afforded initially by the ENIAC computer, we have Roslin Carney. But this was precedence in 1922, imagined by Richardson, which is one of the fathers of the prediction, which in 1922 only imagined to make a computation with a parallel that's computed by human computers instead of processors. And now we come to today, which we supercomputers. To afford this kind of problem, huge dimensionality, we see here that one grid that makes weather forecasts is composed of a certain number of variables multiplied for all the points, which are 10 at the 7 or at 8 power. These are the number of freedom of a problem. The data assimilation can arrive to assimilate data for one or two or less this huge number. So we have a system which is always unobserved. The applications are also at least. We should write to model also systems like this. This is a supercell developed in 1996 in New Zealand and created several labs also. This is the task of Llama. Make correct for situation of this kind, and obviously to make more and more better focus on this, Llama needs also the development of better methods to make data assimilation. The development of the techniques is also based on the work on simplified models, which allow to avoid the huge dimensionality and to use the computational resource to focus on the main problems of predictability and assimilation. This is a paper of Florence in which he describes how to build up all the models able to simulate the main nonlinearity of the problems. Obviously, depending on the problem, the physics we put inside the model is different. But the recipe is very clear and generalizable. He, in this paper, was saying that when he began to study meteorology was a subject with many questions and few solutions. This is the problem. The Navier-Stokes equations have no simple solution, and you can have a solution only in particular case with the sample hypothesis. And so the possibility to use computer resources to make run center of the system is a very precious element. If you have a lowest dimensional model, it's perfect because you can have more runs. The SIP is this one. You can have these terms linear, and constant. You can discretize, or you can introduce orthogonal basis function. As an example, the Renard convection problem has been solved with an expansion in sinusoids, and then Lorentz, as an example, took the three lowest terms, which are irregular periodic solution. And this is the known Lorentz model, which has been produced in this way. Another model that Lorentz has used in his studies is this one, the Lorentz 96 model, which has an advection term, a damping term, and an external force, which resembles the evolution of Rossby waves in the system. The Rossby waves and both this model have this characteristic: to speed towards the growing number and phase speed in the opposite direction. This is a diagram which shows you the evolution. These are the sides. This is the time. The red is the crest, and the blue is the lowest values of the waves. You see the waves that go towards the lower number, which is the phase speed, but you see also some irregularities that travel with the group speed. Adaptive data simulation. Here comes out the work that I tell you. This is a PhD, a master thesis, which see the collaboration of me and with Franco Magnoli, trying to implement data simulation approaches, trying to study the adaptive data simulation of the system. The results that we have found are summarized in this way. The first step is construct a structure for forecasting of Lorentz scientific model, very similar to the production of forecasts with data simulation in the operational activity. One thing that emerges is that if you make the operation of data simulation made with the numerical twin experiment logic. So you have a run which simulates the reality, from which you make measurements, adding noise to resemble the observation error, and you assimilate this data. If you make a simulation in this chain with too far apart windows, you cannot control the system because the system, the Lorentz system, goes away from the reality. If you make with narrow windows of forecast, you can follow the system and you do not lose this behavior. This is one way where the forecasting can be performed reliably. And in this case, if we make forecasts this 15 days, and we assimilate on the wall ring, we have this result. The errors go in this area, and so we have good forecast in the first instance. If we simulate the presence of regular observation network in the continent and the ocean has no observation, we have this situation. And you see here, with the group speed, the undetermination from the ocean, we have periodic boundary condition, so this is caused here. You see here is the speed, or the group speed, that brings the information, the non-information, the lack of information inside. If one analyzes the divergence of the system with the breaking system, so we have the forecasting run, a perturbed forecasting run with a little perturbation, grows its difference with the original not perturbed one. If we repeat the breathing cycle several times, every time we escape the perturbation to the initial data, but we leave the vector to align on the most unstable direction inside the system, we can measure the rate of growth of this type of instabilities to have an idea of the instability of the system and to make a simulation in that point. So these are the results obtained making this kind of experiment. Here we have on the ocean only one observation assimilated. We have two observations assimilated. 4 observations assimilated in fixed points, then adaptive assimilation strategies that we have elaborated during the work of thesis. This is the bed vector. So we assimilate 4 positions where the bed vectors are more unstable. and we have this tracer. If we make a random selection of the position, we have, in this case, a single little better tracer. If we make this kind of strategy, it's a strategy which composes the instability with the no repetitivity. That is, we assimilate in some places, but we do not repeat the assimilation in the same place. We go to search another place with instability. We have to assimilate one day. And this is the result, which is the best one of all the results. But if we consider a different approach, the precedent approach was the extended Kalman filter, which is the better. But for logical operational activity, we must move to the ensemble Kalman filter. We see here that also the random approach have problems. The only approach which has good results, which are very similar to those which are simulated on all the sides of the ocean. Here we have only 4 sides. We have 20 sides simulated. We see that combining the red vector and the not reproduction constraint, we have a very similar result. So this is one of the main results that the basis brought up. This is the slide that summarizes the problem. With the extended Kalman filter, we have must diagonalize the problem with very huge diagonal matrix in the real forecasting service. With the ensemble inside the forecast, we must make a computation with very, very lower dimensionality. This is the motivation. Well, this was the very last projection, which is a link of much of the things that we have seen this morning with the fact that also weather forecasting, the machine learning is entered in a very huge way. And here I summarize works that are outside what I've done. They can be also afforded with this kind of Lorentz system in which we have more scales coupled together and inserting instead of the parameterization of the sub scales that we studied here, use neural network to make the study of this kind of dynamics, which are the more literal behavior dynamics. This one, as an example, the many that are present now, a workshop combined between the SMWF and ESA, in which we spoke about machine learning and their system observation to make predictions. So the systematic is very relevant for weather forecasting. Many applications of machine learning are foreseen for the future of the weather environment prediction. And as an example, projects devoted to make a seamless system for Earth modeling is strongly linked to the development of machine learning approaches. So as also private initiatives are focused to make this kind of jump from model to physically based models to machine learning approaches of data simulation. Then, conclusions. We have made a review, a very rapid review of many things regarding mathematic scales, numerical modeling, and data simulation. We have seen that with low order models, we can make studies which have a didactic value, because during the next entering contact with many of the problems which are the very problems to be afforded to make weather prediction. And this is the part which is interesting for Llama. Llama is interested to allow the group of young researchers, which could be very useful to give contribution to operational services that Llama is devoted to develop. And then we have also seen interesting results. We see that the best results we have seen are for the ensemble Kalman filter, which is the one which is widely providing realistic numerical and optional prediction. The other activity may be devoted to the applied exploiting the new generation of nodes, which can be applied to go to make data where it's needed, and then we have machine learning for the future of the atmospheric prediction.
Questions?
Use the microphone, otherwise.
I have a question regarding how you simulate systems without the machine learning approach. In the sense that are any techniques that are hardware-based used or not? In the sense that in machine learning, I mean, it's very efficient because people have figured out how to accelerate the calculation of gradients and so on and so forth on GPUs. But you can do, I think, similar things also for different kind of operation. So in order to simulate such a huge system, are also some kind of hardware accelerated techniques involved, or is it just computations on CPU and that's it?
Use the Python. Working.
The classic approach is to implement the equations, discretize the equation in the processors and go hardly with the computation. So this is the history now, and that still now is performed in this way. The models which we use in Consortium Llama are developed in this way and run on parallel clusters running with what you think about hardwired modeling. But the future, which is the one which is searched now, is also to exploit machine learning to increase strongly the potentialities, and so to use GPUs for making these computations and so on. Because if you go backward a little bit, sorry. You see here that this is a private institution, but the idea is to arrive here to exploit this kind of strongly increased potentiality of the computational system using also GPU and the methods developed for machine learning to increase the resolution of the simulation, because the intention now also to make this kind of approach, the digital twin of the Earth, is to model all the scales, every kind of dynamics at the right scale. But to make this, it is needed to manage correctly the computational power to exploit machine learning to increase the resolution, especially of the smaller scales.
Any other questions? I have a question, general one. There are many on problems that limit the accuracy of prediction. Is there one specific area where one should work hard in order to get a significant improvement? The grid in the scale, or the accuracy of simulations, measuring other variables, and so on. Is there a critical area?
The critical are several, so you must work on several areas. So you must improve the data that you connect with the observation system, so you must work on them. But also the increase of resolution is very relevant, and this can be achieved now only with a relevant increase of computational power. And part of the solution is the one that I have described for the question. Another point which is relevant is to increase the capability of the data simulation systems, which they have been developed mainly for the intermediate scales, but the data simulation for very detailed scales are still to be better developed. As an example, in a center like Llama, data simulation is not simple to be implemented. It is the difficulties to work on a very unstable system and very detailed, like the supercell I've shown, brings the problem to be very, very difficult to be afforded. So only very few local centers are capable of making data simulation on the very detailed scales. We are working on this at Llama, but we have not a data simulation, an operating data simulation system just for this problem, because the smallest things are very delicate and very difficult to take also from the point of view of data simulation.
Okay, thank you. Let's thank you. Let's move on to the next. we are going to change subject. We are going to biophysics. So, as you see, the next speaker is Valentina Bonfiglio. The title you can read yourself.
Good morning. My name is Valentina Bonfiglio. I'm a PhD student in molecular medicine at the University of Siena. First of all, I would like to thank the organizer of this event for the possibility to share my work. Today, I will talk about the way it is possible to characterize the mechanics of a biological system with a stochastic approach. In particular, I will discuss an application, cell contraction, and I will show you how we developed a stochastic model in order to make parameter estimation from experimental data from a small ensemble of myosin motors. I will brief the biological background of our study, which is the contraction of striatal mass. The structural and functional unit of striatal cells is the sarcomere, and in the sarcomere, the production of force is generated by ATP cyclic. Can I have the other microphone?
Try to switch.
Yes. Thank you. Yes. Okay. In the sarcomere, the contraction is generated by ATP-driven cyclic interaction between the myosin motors emerging from the thick filament and the actin monomers in the overlapping thin filament. Here you can see a schematization of the image above, with the thick filament in black, the thin filament in gray, and the myosin motors in red. I will talk about myosin motors or molecular motors, and they are essentially the same thing. The production of steady force in the sarcomere is generated by a collective motor generated by the mechanical coupling of all the myosin motors bound to the filament backbone. And despite the bulk of data characterizing the mechanokinetics parameters of muscle contraction at the cellular and tissue level, the definition of these parameters at the molecular level is still incomplete. And this is because of the complexity of the arrangement of molecular motors in a three-dimensional structure in the sarcomere. So cellular level studies cannot reveal the details of this mechanical coupling, also because this collective motor is difficult to isolate from the contribution of other cytoskeleton and regulatory proteins. On the other hand, this collective mechanism is not revealed by single molecule mechanics experiments. And for this reason, we investigated the performance of a synthetic one-dimensional machine containing the minimum number of molecular motors needed to reproduce this collective behavior in the muscle cell. I will briefly describe the experimental setup that allowed us to obtain these data to investigate the production of force at the molecular level, starting from the synthetic machine assembled at the Physiolab in Florence. This synthetic machine is an ensemble of myosin fragments deposited on a surface in interaction with a single actin filament, and the actin filament is attached to a bead trapped in a focus of a dual laser optical tweezers. The actin filament selects a functional one-dimensional array out of the myosin molecules, And the output of the nanomachine is measured by the dual laser optical tweezers, which act as a force transducer, while the support carrying the myosin fragments acts as a displacement transducer. To implement the condition for isometric contraction, the data has been acquired in length-plan control, during which the distance between the bead and the support is maintained constant. Therefore, this minimizes the track compliance that the motor perceived, approximating the compliance that we actually perceive in the muscle. This allows us to recover the fluctuating time series of the force, characterized by individual attachment and detachment event of the myosin motors in interaction with the actin filament. So, under length control in physiological ATP concentration, the system is able to express isometric contraction that induce the force development from a condition with all the motor detached up to a stationary state, which is called the isometric plateau, characterized by this cyclic individual attachment and detachment event of the myosin motors and the actin filament. The aim of the study was to analyze the time series of the force, both the transient dynamics and the isometric plateau, in order to provide, through a process of reverse engineering, an estimation of the force of a single molecular motors and other interesting parameters like the duty ratio of the system, which is the fraction of the motor actually attached to the actin. In order to do that, we solved the population dynamics, then we calculated the probability distribution of the force of this small ensemble of motors, and then we performed an optimization procedure in order to provide an estimation of the relevant parameter of the system. According to the geometry of the nanomachine that I described earlier, the number of available motors in the model is fixed, and the system is composed of n equals 16 molecular motors. Due to the small number of elements in this system, a correct framework of work would be a stochastic approach. Each motor can be found in different configurations based on its interaction with the actin filament. We have a detached state, D, and two different force-generating attached states, A1 and A2. This microscopic dynamics is described by this scheme of chemical equation, where a detached motor in D attaches itself to the nearest actin monomer. Then, following the state transition A1, A2, the motor undergoes the working stroke, which accounts for the generation of force, and then the motor detaches itself from actin. The transitions between different configurations are characterized by the chemical reaction constants, K1, K-1, K2, K-2, and K3, and they represent probability per unit time that the single reaction occurs. This microscopic dynamics is Markovian, therefore we are able to write and solve a master equation in a form that I will show you in a moment, a master equation that describes the evolution of the state of the system. At any time t, the state of the system is described by this two-dimensional vector containing the number of motors N1 and N2 in the force-generating configurations, while the number of detached motors can be obtained at any time by a conservation law. As I was saying, we consider the master equation in this form, where Q is the stochastic matrix that governs the dynamics of the system, because it contains the transition rates of all the possible transitions between different configurations. Thanks to the very small number of elements in the system, we were able to solve the master equation without approximation. And the solution of the master equation represents the probability of finding the system in the state n at a time t, and solving for p of n and t, one can recover the mean value of the number of motors in each configuration. Then we calculated the total force of the ensemble exerted by the ensemble of motor by simply assigning to each motor the force that it is able to exert based on its configuration. Since we have access to beautiful experimental data that allows us to calculate the distribution of the force around the isometric plateau, we wanted to calculate this, to compute the distribution in our model in order to compare the two. And we follow this approach. The total probability distribution of the force of the ensemble would be resulting by the sum of different terms. For simplicity, let us consider just one of the two populations of force-generating motor, and we need to take account different contributions. First of all, we consider the situation in which we have just one molecular motor in a force-generating state, and this motor is able to exert a force that is uniformly distributed in a given physiological interval. This term will contribute to the total probability distribution of the force with the term pi1, which needs to be weighted with a stationary solution of the master equation that represents the actual probability of having just one motor in the force-generating configuration, which is rho1. If you consider then the probability of having two molecular motors in the force-generating configuration, therefore the stationary solution of the master equation for n equal to 2, this term will weight the distribution of the force pi2. And so on, we can consider the probability of having 3 motors in the force-generating configuration, and up to n equals 16, meaning all the available possible molecular motors. When we consider all the contributions properly weighted, we obtain, for a given choice of the parameter of the model, a distribution like this that we can compare to the actual experimental one. Here you can see the result of the fitting procedure and the parameter estimation. First, we validate the fitting scheme against synthetically generated data with the Gillespie algorithm, and then we apply them to the experimental data of an ensemble constituted by 16 myosin motors purified from the rabbit skeletal muscle. And from the master equation, of course, you can recover the mean field description of the system, meaning the differential equation that describes the evolution of the system in the deterministic limits when we do not take into account the contribution of the fluctuation of the force, and these equations are easily to solve, and we use this equation to fit the development of the experimental force, and we recover the rate of force development, but this approach does not really solve the problem, and it leaves us with an indeterminacy that I will show you in a moment. Here you can see the probability density function of the total force at the isometric plateau in this area. And these are the fluctuations of the force around the mean value of the force exerted by the ensemble. Here you can see the result of the fitting the parameter estimation for the force of a single molecular motor on the x-axis, and the duty ratio R, which is the fraction of motor attached to the actin. And as you can see, the solid line represents the solution of the deterministic model when we neglect the effect of the fluctuation. And the problem with this approach is that this equation, relying only on the mean value of the total force of the ensemble, we obtain possible solution for the product of the two parameters, the force per motor and the duration, but we cannot extract them individually. While taking into account the distribution of the force around the isometric plateau, meaning formulating the problem in the stochastic approach, we were able to solve this indeterminacy and actually select a single value for each of these 6 data sets. Just a last comment, all this procedure has been done with a fixed system size, n, meaning the number of available motors for the interaction. And these numbers were estimated independently by measurement of the rupture events of the myosin motors in rigor, meaning in ATP-free solution. But we can also estimate the force per motor for different values of the system size. And as you can see, the optimization procedure converges only for a small set of values around the value n equals 16, which was obtained by these independent measurements. In conclusion, this synthetic machine is able to reproduce the functional behavior of skeletal muscle myosin, and accounting for the role of fluctuation stemming from the discrete nature of this small ensemble of motors, we were able to interpret the experimental data in a stochastic framework. And with the reverse engineering procedure, we were able to recover single motor properties by the analysis of the behavior of the ensemble. Furthermore, this approach, we hope it could pave the way for the study of the performance of unknown myosin isoforms. And with that, I would like to thank all my supervisors from the Department of Physics and the Department of Biology, and all of you for your attention.
Okay, questions about these experiments and perspectives? So, what next? I mean, what is the next step?
Actually, we tested the data that I've shown you comes from skeletal muscle. This comes from myosin, purified from rabbit soleus muscle, which is a slow muscle. And actually, regarding skeletal muscle, we are, during these days, analyzing the data from another muscle, also from the rabbit, which is the psoas muscle, which is a fast muscle. And we expected to find different, very different results for the force per motor and the duty ratio. We expected this fast muscle to have a lower duration and a higher force per motor. This would be interesting because it could provide really a way to test known isoform, meaning these isoforms come from healthy animals. But if we deal with mutated isoforms like from a disease, or also, yes, like mutated from a disease, these are unknown isoforms, meaning we don't know anything about their kinetics and the force per motor, and sometimes we don't know if the problem with a certain disease is that the sarcomere is unable to exert the proper force, or if it is not able to perform, to exert its force in a stationary state, meaning that the duty ratio could be too low, the number of force of myosin attached could be too low. So it would be interesting to disentangle these two parameters for the performance of unknown muscles.
Thank you, very interesting. So, question, and we can thank the
Sì, sì.
Okay, so now going to the last speaker of the morning session, Simona Olmi, and she's going to talk about neuroplasticity.
Okay, let me start thanking the organizers for giving me the possibility to speak. And I'm presenting a work that I've done in collaboration with my former PhD student, Al Gurtaer, and Alessandro Sorcini, that will also speak about exact neural mass models in the afternoon. As you can read from the title, I will lead you in the world of working memory. So let me simply start introducing the meaning of working memory, so introducing the field where the talk will move around, let me say. So working memory can be thought as a working system, so it is fundamental in our everyday life, since it is fundamental when we have to solve a task or achieve a certain goal, a desired goal. Thanks to the working memory, we can say that information in our brains can be rapidly stored, maintained, but also processed and rehearsed, so recovered. Up to now, we can, all the experiments that have been done in order to gain insight the working memory, so to understand which are the mechanisms underlying the working memory, are done as behavioral experiment, and I will enter into the detail of what does it means in the next slide, while all the data are recorded through the electrophysiology. So usually the kind of behavioral experiments that are done are called the delayed response task. Usually during this experiment, the subject, that could be a human or an animal, is trained to solve a task. Usually, as you can see here, during the delayed response paradigm, it is presented a sample, so a sample to the subject, then the subject is left alone, so a certain delay time passes between the presentation of the first sample and the presentation of a second sample, which is called the test sample, that could be equal to the first one presented or different to the one that has been presented. So essentially the subject has to say if the second test is equal to the first one or not. This kind of tasks requires, as you can imagine, the short-term storage of information, because you have to remember if the first task that has been presented is the same as the second one. And usually some kind of measurements has been done. So we speak about the possibility to measure spike trains or local field potentials if the task is performed by the human, because it is possible in this case to do some electrodes implantation. Otherwise, if the human is the subject which has to solve the task, usually you can see it wears the cap and the electroencephalography data are taken. The first experiments to get inside the working memory mechanisms has been performed by Alexander in 1971, and they were essentially single unit recordings in monkeys. They realized during these experiments that when the sample is presented, it evokes increased firing in the brain activity of the subject. So they noticed an enhanced activity that persists also during the delay period, so during the time in between the presentation of the first task and the second task. So the working memory, according to these experiments, was believed for a long time to be maintained thanks to this persistent activity. But somehow this paradigm that is called the paradigm of persistent state, so where the memory is kept thanks to high firing rate activity, has some pro, as you can imagine, but also some contra. And the problem in this case is that it has a high metabolic cost. So it is difficult to think that memory can actually be taken into account in a persistent activity regime, since it has a really high metabolic cost. Then there are some debates regarding data processing artifacts where I do not want to enter today, let me say. Starting from this, so from the fact that there were posed some problems regarding the actual possibility of the persistent state as the explanation of working memory, some new approaches have been performed in time. And what I want to speak now is the new approach proposed in 2008 by Mongillo and co-authors, which is based on synaptic facilitation. So what does it mean? What Gianluigi Mongillo, Omni Barak, and Michel Zolix has presented essentially is a synaptic theory of working memory, in the sense that they have taken advantage of short-term plasticity to explain the possibility of keeping, memorizing items, and retrieving information. In particular, when a cue, so a sample is presented, it triggers both depression and facilitation, where the facilitation will be the one responsible for maintaining the working memory and allowing the subject to select the items, while the depression underlies the explanation for population burst activity. In particular, in this paper of 2008, the authors have used the spiking network models to explain the working memory mechanisms, and they have proposed a simplified heuristic rate model just to do some calculations. What I would like to say, since I'm in favor of in the rest of the talk, you will see that I'm in favor of this new paradigm, of this new explanation, that it has some more benefits than the previous one based on the persistent activity, since working memory in this case can be maintained also in the absence of spiking, so it does not have a real high metabolic cost to be maintained in this formulation, since essentially the population in this case are the population bursts that somehow allow for interference-free storage, and they do not appear continuously. They simply appear the population burst, as you can see when you retrieve an item, you retrieve a memory. What it is important to notice, so the one message of this model, is that all the information is represented at the macroscopic state, since we are speaking about population burst. So for those that are not familiar with this language, population burst is the contemporary and synchronized activity of all the population of neurons that fire at the same time together. So it means that they are all involved in the activity, and at a certain time they somehow they fire at the same time. So they are active at the same time. And if we measure the population burst, we are really measuring a collective microscopic activity at the level of the entire network. And this is good because, as you remember from the first slides, the kind of data that we can take during these experiments are local field potential, or EEG signals, that are macroscopic signals. So it is possible to compare directly the model with the data that are taken. What I'm going to present you to show now is somehow to use a better model than the one that's been introduced in 2008, which somehow is still based on short-term synaptic plasticity, which is able to exhibit spike synchrony as this one, but which will allow us to measure to access the measures that are used in the experiments, like the EMG and the local field potential, since all the models that have been used previously somehow were based on rate models, and so they do not have direct access to the measures, to the data. So I do not want to enter into many details of the model that we are using, since also Alessandro will speak more in detail in the afternoon. But let me just say that from a network point of view, we are going to use quadratic integrated fire neurons. So the neurons in this case are described by a mean field potential V, which is subject to a first-order differential equation of this type, where eta is the heterogeneity inside the network, J is the coupling among the neurons, and R is the mean firing rate that takes into account the spiking activity, so all the spikes received by the single neuron into the network. So it is possible to write down a system with equations if we take into account the network, but and this is the main feature of this model, that it is possible also to write down an exact mean field of this model in the limit, or in the infinite size limit. It has been shown by Monpriot, Poisson, and Rox in 2015 that it is possible to write down some the so-called exact neural mass model, so two equations that takes into account the dynamical evolution of the mean firing rate of the network and the mean membrane potential of the network. So from a computational point of view, we pass from simulating a system of n equation, where n could be potentially very large, to a simulation of simply differential equations describing the average activity of the network, firing activity of the network, and the average mean membrane potential of the network. So to this, we are going to add the evolution of the depression and the facilitation, where you can see they act in this way. Whenever we have a spiking activity into the network, as you can see from the dynamical evolution of the rate of the network, of the firing rate of the network, you see that the depression decreases because it takes into account the resources that the neurons have, so they have a limited amount of resources, and if they fire, this kind of resources are less and less available. On the other hand, whenever you have a firing activity into the network, the facilitation increases, because a neuron that fires more, in the sense that is more and more involved into the activity of the network. So including also the equations for the depression X and the facilitation U, we come into a system of 4 differential equations. So we simulate essentially the activity of the mean firing rate of the network, the mean membrane potential of the network, the mean depression of the network, and the mean facilitation of the network, where the assumption that has been done to get the exact neural mass model are still valid, so we can still affirm that we are using an exact neural mass model. The fact that this exact can be seen from these slides. So here we have simulated the network, so the original network system, in 2 different initial states. In this one, where you have some firing activity as a following, as a response of presenting two successive stimulations with an external current, and then you don't have any other kind of activity. In the other state, the presentation of the 2 subsequent pulses, external pulses, gives rise to a periodic state. So these are the simulation results, the experimental simulation results, and you can see the mean field results perfectly overlapped with what we have seen before. So let me go to something that could be more interesting and analyzing the case of a simple neural network. So in this network, we have coupled two excitatory population and one inhibitory population that acts as a common pool. So let me just spend some minutes on this figure because then it will be more clear to explain what happens into this kind of system. Both the excitatory populations have connections that are weighted with the synaptic plasticity, while the inhibitory is not subject to short-term plasticity. All the three populations feel an external background current, IB, which is the same for all three networks, but we have designed the system such that the two inhibitory currents can receive different external stimulation currents. So the one that impinges the first excitatory population is different from the one that impinges the second excitatory population. So if we play with the external background, we see that we can gain different situations, and we can load and retrieve some memories using different background states. So in the first case, I'm simply loading an item in the first population, the population blue, as you can see also from the color codings. So if I load an item giving an external stimulation to population 1, I see first a spiking activity into the network. And then when I give a second pulse, which has a smaller amplitude with respect to the first one, I'm able to retrieve the memory, because you see that the network response is this one. It gives rise to a new population burst, so a new collective activity. If I do the same onto the second population, so if I do the same retrieval current, small current, also to the second population, I don't see any kind of activity, because in the second population, the item was not loaded since the first external signal was not given. And from my mean field point of view, you see that corresponding to the raster plot, so to respond to the activity of the network, you have a periodic activity into the firing rate, and consequent the decreasing activity of the depression and enhancing of the facilitation. We can load an item also in another way. In this case, if we change the background current, we see that when giving a pulse, an external pulse to the population 1 jumps into a high firing persistent activity that stops just when you decrease the external background current. In this way, you are able to retrieve the item, to store and retrieve an item, because you see that then it starts going, giving periodic oscillations. As before, since in the second population no item was loaded, so no stimulation was given initially, the second population remains silent, so unable to store and retrieve the memory. Finally, let me show also this third possibility to store the item. In this case, giving the input, you see that the system starts oscillating periodically, and so this is also a third possibility to store an item. So the point of using an exact neural mass model is that what you see, you can explain what you see from the numerical simulation by simply performing a bifurcation analysis. So, for example, just let me show the third case. So in the third case, for this value of external background, you lead You lead the state from a fixed point here, which is the initial value of the ground current, to the point here, where you have a periodic activity. So this means that you are leading the state from a steady state point of view to a periodic state. That's why you are able, for this value of the background current, to observe a periodic dynamic. So this is just to say that we can somehow take advantage of using a simplified rate models, because we can perform a bifurcation analysis and so play also with the parameters in a conscious way. So here, I would like to somehow to introduce some comparison with the results that we can get numerically with some experiments. So, for example, here I just want to show the, let me say, the possibility to get to explain as you can see. Somehow, when you load an item, so you give a gradient of synaptic, you give somehow an external stimulation, you observe that the firing rate is oscillating. So the response of the system to an external stimulation is a transient oscillation. And transient oscillations has been observed also when the items are loaded in the prefrontal cortex of the monkeys during memory task. So as you can see, these were the experiments that I was mentioning, where you observe doing the spectrogram some activation in the frequencies in between 16 and 32 Hz, and you have some bumps of activation for lower frequency. And performing the spectrograms of the mean membrane potential, you can find the same kind of frequency activation. So just to say that what is the mean membrane potential. Mean membrane potential oscillations that are macroscopic oscillations. So we are using a model which is valid in the thermodynamic limit, where we cannot say that the oscillations that are present are simply fluctuations. So we are sure that what we see, the kind of oscillations that we see, are those that are related to the macroscopic signals and the experiments we can take. In this case, we see, as in the experiment, that we have a delta band activity which is locked to the stimulus onset, and the sustained beta band activity which is related to loading the item. Let me skip the second example and let me simply go to something a little bit more interesting. So if you think about using a bigger network, because in the previous slides I simply used a three globally coupled network, we may think that more items can be loaded. Because if you have simply two populations, at least you can load. Sometimes it's working, sometimes not. Okay. You simply think that you can load one item or two items due to the fact that you don't have more than two populations. And actually, it is possible for some parameter regions to load two items at the same time in a small three population networks. So, what happens if we increase the number of populations? Are we able to load more than two items, for example? So, in the following, I'm trying to show you what happens if we couple 7 excitatory populations plus 1 inhibitory pool. Okay, in this case, let me show you the picture. So we are using 7 populations. Each population, as before, is coded by a color. And this is the raster plot of the network, which means I'm just reporting the time with the dot, where a single population emits a population burst. So here, as you can see, I'm loading an item into the population 1, the blue one, which reacts, as you can see from the signal of the firing rate, with a fast activity, and then it starts oscillating periodically. To each population burst, to each oscillation, I report a dot here in time. Then I try to, in order to see how many items I can load, I'm loading an item also in the second population, the orange one, and that's before I see fast activity during loading of the item, and then the system allows for a periodic regime where the two activities, the activities of the two populations are in antiphase. If I load a third item in the third population, the green one, I also see during the loading a fast activity that somehow stops the activity of the other two populations, and then the system sets in an antiphase periodic regime. And if we perform the spectrogram of the mean field into the network, we can see many possible frequency bands emerging. In particular, we observe a delta band. You can see activity upon the item presentation, but we also observe, as you can see, whenever a fundamental memory cycle, F cycle here, and its harmonics, that is related to the period between one collective spike and the successive one, but we observe also the frequency which is related to the bursting activity when the item is loaded, and the resonance. We have a main peak and the resonance around 30 Hz. So we have a big activity in different frequency ranges that can be somehow observed also in the experiments. But as you can see, if you, in order to understand and to answer the questions that I posed before, in this kind of setup where we have a certain population, we are able to load just 5 items. So for a certain moment, we are able to load the sixth one, but then the other one stops, and then the system is able to keep track of just 5 items. And this is not well, this is not obvious, but this is also not always the case that we are able to load the 5 items, because if we try to present the items with a different velocity, so this means that the presentation, instead of happening to the first one here and to the second one here, may happen more faster, so you can load the items one after the item more strict in time, more fast in time, or more slower in time. So you will see that if you present very slowly one after the other the items, you don't always have 5 items that are loaded, and this is true also if the presentation is very fast. So there is just interval in the presentation rate where you are able to keep at least 5 items. And you see that if you take into account also the serial position, so which are the items that you memorize depending on when you present them, you see that if you, for short, when the presentation rate is very slow, you see that you are able to memorize just the last ones. In the intermediate regime, there is not a big rule emerging, while if you present very fast all the object, at the end, the subject usually memorizes the first one that are presented and the last one that are presented, so forgetting all the items that are presented in the middle. And this can be seen also taking into account the probability of retrieval. So for example, if we take into account the regime that I call the slow presentation rate regime, you see that the last one that you present is the one that you remember with 100% of possibility. And the sixth one that has been presented also is memorized with 100%. So but the other ones that are presented first are less probability of retrieval, just going to 0. We can do the same for all the other intervals of the presentation rate, and we see essentially that for slow presentation, as I've seen, the last item is retrieved, and this is called recency effect. On the other hand, if we are into if the presentation is very fast, the first and the last items are those that are retrieved, the so-called primacy and recency effect, while in the intermediate rate, we can get the maximum capacity, which is reached, and this is, but we have a less, a minor recency effect, and this is in agreement also with many results that have been found in the literature, where the maximum capacity is usually in a range in between 3 and 5. If we look at the details of the maximum capacity, we can see that from a mathematical point of view, it depends on the parameters of the system, but since the time is finished, I will not enter into the details of this, and I would just summarize what we've presented is somehow a very simple model, which is able to reproduce fundamental working memory mechanisms, since it allows us for using and simulating the, let me say, the mean brain potential that can be compared with the experiment. So somehow giving a plot with respect to the other heuristic models. Okay, thanks a lot.
So, open to questions. Do you remember the beginning of the talk?
I see there.
Okay.
Thank you. Very interesting. Model you use for the neurons in each population? I didn't get it.
Ah, okay. It was too slow the presentation, so people in the audience does not remember the first slide that I presented.
Leak integrated fire.
Yeah,
okay.
the quadratic integrated file,
quadratic.
which is different from the leak integrated file that you cite from the fact that here you have a quadratic term instead of a linear one. Like the leak integrated file is a spiking neuron with a threshold, so somehow it's a simplified model that does not reproduce the production of the action potential, but is simply a a signal that somehow rises, and then you put a threshold, and you say that after this threshold, the neuron emits a spike, but the spike has not somehow a physiological shape, is a simplified signal.
Does this mean the fact that it's quadratic is crucial, right?
Yeah. It's crucial for the application of the mean field, so for the resolution of the mean field equations and to derive let's say, the neural mass model.
Other questions? So, if not, we can thank the last speaker.